Hello, I'm Surya. This is Lab 3, the magnetic field of a permanent. So the purpose of this lab was to calculate the distance dependence of the magnetic field due to a bar magnet. We will write code to represent the magnetic field due to this bar magnet and compare this to the experimental value to see how our code compares to the actual experiment we did. And then finally, to characterize the magnet we were given and its magnetic field using physics principles. So some fundamentals. One is the Biot-Savart law, which relates the magnetic field to the magnitude, direction, length, and proximity of the electric current in one equation. So we kind of use this to derive other equations in our lab. So we have the distance dependence of a bar magnet equation, which is the magnetic field of the bar magnet is equal to K, which is a bunch of constants, times the distance to the number n, and we will find this number n later on. So this equation can be rearranged using natural logs to the natural log of the magnetic field is equal to the natural log of k plus n times the natural log of the distance. So for the actual experiment, we used a Tesla meter app, and we calibrated the sensor and set up the magnet as per the lab instructions to calibrate for true magnetic north. And then we recorded the on-axis distance needed to get an x component of the magnetic field of 20. So for the off-axis magnetic field, I found a distance, d perp, where the net magnetic field had a magnitude of 100 microteslas. I recorded the y component of the magnetic field here, and then I moved my phone upwards the same distance d perp, so I created kind of a right triangle there with the diagonal of distance d. So I adjusted for the... So now for our data and calculations. So on the right we have a graph of the natural log of the magnetic field in the x direction versus the natural log of the distance. And this gave us some points which generated a line of best fit of y equals negative 3.5x times negative 3.5x minus 14.87. So this is kind of our y equals mx plus b format. And again, like I said earlier, we have a equation that resembles y equals mx plus b, except in our case, the mx is n times the natural log of r. So in this case, n would be equal to negative 3.5584. So that is what we have for the value of n. So using that and using our equation, we can solve for mu. So doing some algebra basically with the numbers that we got in the equation, we can get mu to be 1.737 ampere meter squared. So then on the left side here, we have our off-axis results. So we got the off-axis result to be 0.000032 in the x direction, 7.866 times 10 to the negative 6 in the y direction, and negative 3.1 times 10 to the negative 5th in the z direction at this 45 degrees point. So next we have the coding, and we started from the starter code, and then I inputted my value for mu, and then I created a magnetic field function that I would actually use to create the arrows for the magnetic fields both on and off axis. So I also have scale factors here that help define the size of my arrows. And here we have the results of my experiment. You can see all the results for the magnetic fields both on and off axis, and on the right, you can see the on-axis magnetic fields are represented by the orange arrows, the off-axis fields are represented by the blue arrows, and the 45-degree field is represented by the small green arrow. So the theoretical value of n, the distance dependence, was 3, but from our graph, we determined that this was 3.5584 in our experiment, so the percent error was 18.6, which is not too bad. So our experimental magnetic field at 45 degrees had a magnitude of 3.2 times 10 to the negative fifth, but our calculated value had a magnitude of 1.72 times 10 to the negative fifth. Um, this is fairly different, and I tried the experiment a couple times to see how close I could get, but this was the closest I could get to this value. Finally, the conclusion what if questions. So, what if we hadn't oriented to compensate for true magnetic north? So, the graph would look the same, basically, but this would cause a large difference between the theoretical and experimental values that we got. And what if we'd stuck two identical magnets together and run the experiment again? I would expect that the magnetic field at each location would nearly double that of just one bar magnet. Thank you for listening to my lab.